In 1967, physicist Hans Bethe won the Nobel Prize in Physics for his discovery of the nuclear processes that generate energy in stars. The process is nuclear fusion. The Sun, like most other stars, are fusing hydrogen nuclei into helium nuclei. Fusion is the process of putting light nuclei together to make heavier nuclei. To do that, nuclei have to get close together, close enough that the strong nuclear force can snap them together. The catch is that nuclei have protons in them, and thus all nuclei have a positive charge. Like charges repel one another. Although the strong nuclear force is stronger than the electromagnetic force, it has much shorter range than the electromagnetic force. The nuclei still have to get very close together. In order to get close enough, they need to be traveling at high speeds. The core is the location where the temperature of the Sun is highest and thus where nuclei are traveling the fastest average speeds. Also, because the core bears the weight of the rest of the star on top of it, the pressure is extremely high and gas is compressed to very high density. The core density is 10 billion times denser than at the surface. This high density means there will be lots of particles in close proximity to undergo fusion. The Sun generates almost all of its energy via the proton-proton chain. That chain is illustrated here. The illustration shows all the reactions that are involved in creating a single helium nucleus. There are some other side reactions that also occur, most of which are unstable or don't result in much energy, but the proton-proton chain is by far the most dominant process. It will help to remember that a hydrogen nucleus has only a single proton. The left and right branch at the top are identical. Focusing on only one of them, the first step involves the fusing of two hydrogen nuclei. This results in a decay process that turns one of the protons into a neutron and emits a positron, which is an anti-electron and an electron neutrino. The resulting nucleus is called a deuteron, composed of one proton and one neutron. The emitted positron will quickly run into an electron and the two will annihilate each other, giving off a pair of photons. That interaction isn't shown on this diagram. The next step involves the deuteron picking up another proton, forming an isotope of helium called helium-3. The two helium-3 nuclei finally come together, forming helium and kicking off the two excess protons. These protons will move away at high kinetic energies to carry out nuclear reactions elsewhere in the core. Though the proton-proton chain takes on average 100 million to 1 billion years to complete, there is a lot of it going on all the time. There are about 10 to the 38 reactions occurring each second. The Sun converts 500 million tons of hydrogen to helium every second. A clue to the physics that describes what ultimately gives rise to the Sun's energy is a comparison of the masses of the initial protons and the resulting helium. Notice that there is less mass at the end of the process. There is 0.7% less mass at the end of the reaction. This missing mass has been converted to energy, described by Einstein's equation, E = mc². The form of the energy is in newly created particles, photons, and the kinetic energies of the particles. Many nuclear reactions involve the emission of neutrinos. The first step in the proton-proton chain involves the emission of an electron neutrino. Neutrinos are very low-mass particles that speed away from the Sun's core at nearly the speed of light. Neutrinos interact with matter only rarely. They can easily pass through a block of lead a light-year thick. Although they interact with matter very little, there are a lot of them emitted. There are 1 billion neutrinos coming from the Sun and passing through your body every second. Even at night, they pass through the Earth and pass through your body on the other side. Because there are so many emitted, we can detect them in neutrino detectors, like the one shown here. These are usually built underground to shield them from other particles that might mimic the detection of a neutrino. They are often filled with purified water. When an occasional neutrino interacts with an atom in the water, a weak photon will be released. Around the reservoir of water are photomultiplier tubes that work to amplify that weak photon and record the detection of a neutrino. We currently detect 10 per day, on average. We know we are only capturing a very tiny fraction of the neutrinos that are passing through the detector. Based on the number we detect, we can calculate how many must be passing through the detector per second per unit area, i.e. the neutrino flux. How do we figure out what nuclear process is at work inside the Sun? We know that the Sun has an output power of 400 trillion watts. We can experiment in our labs to figure out how much energy is released per reaction during various types of nuclear reactions. Suppose we think reaction A is powering our Sun. We experiment and determine how much energy each occurrence of reaction A gives off. We can then calculate how many times reaction A must occur every second to have the resulting output power of 400 trillion watts. Since each reaction will emit a neutrino, we can then check whether the number of neutrinos detected, and the calculated neutrino flux, agrees with that number of reactions. Current detection rates support the assertion that the proton-proton chain generates almost 100% of the Sun's power. Stars larger than the Sun, with core temperatures greater than about 18 million Kelvin, generate most of their energy via the carbon-nitrogen-oxygen cycle. The CNO cycle takes the same input of hydrogen and produces the same output of particles and radiation. Carbon-12 turns into isotopes of carbon, nitrogen and oxygen in the process, but returns as carbon-12 in the end. Carbon mediates the conversion of hydrogen to helium. Though there is an increase in the amount of helium, there is no net creation of carbon, nitrogen or oxygen. High core temperatures are required to make the CNO cycle go because of the greater number of protons in the carbon nucleus. This results in a greater amount of electrical repulsion between the protons and carbon nuclei. Thus, protons have to be moving even faster in order to get close to the carbon nucleus. This graph shows the relative amount of energy produced by both the proton-proton chain, blue, and the CNO cycle, red. At temperatures that are too cold, no fusion at all would take place and one would not be discussing a star. Core temperatures less than around 12 or 13 million Kelvin produce energy only by the proton-proton chain. Stars with higher core temperatures do both. The Sun produces about 1.3% of its energy by the CNO cycle, the rest is by the proton-proton chain. At a core temperature of about 18 million Kelvin, there is a crossover to where more energy is produced by the CNO cycle than the proton-proton chain. This crossover occurs in stars with masses of 1.2 times the mass of the Sun. For stars with more mass than this, the CNO cycle dominates.